So again, continuing with practicing drawing Lewis structures. Again, Lewis structures are important to get right the first time because we're going to be applying this to molecular geometry. Then if we get the molecular geometry correct, we can apply it to polarity. Likewise, if we get Lewis structures correct, we can apply it correctly to hybridization. So it's very important that we draw the Lewis structure correctly. So here we want to know the number of bonding and lone pairs of electrons around the central atom. And we have, for example, iodine pentafluoride. Notice here that the central atom is connected to halogens. And so if we determine the total number of valence electrons, we have 1 iodine plus 5 fluorines. That's 42 electrons that we have to use. Now, a quick way to determine the number of bonding and lone pairs is if you have a central atom bounded to halogens, you can take the number of halogens bounded to the central atom. That's going to be the number of bonding pairs. And then you take the number of bonding pairs multiplied by 8, we get 40. So 42 minus 40 means we have 2 electrons left over. So there's going to be 1 lone pair on the central atom. And that's a quick way to help establish how many bonding and lone pairs you have on the central atom when you have a central atom bounded to halogens. It works the best. And so we deduce that we have 5 bonding pairs and 1 lone pair. Now, if you were to draw the Lewis structure, it would look something like this. So again, we see we have 5 bonding pairs and 1 lone pair on the central atom. Next, we move to silicon pentachloride ion. And here again, we have silicon bounded to halogens. So if we look at the total number of valence electrons, be 4 times 1 plus 5 times 7 plus 1. And we add an extra 1 because it's a negative charge. We have to add 1 electron to the total. So we have a total of 40 electrons. Now we have 5 halogens and each one wants 8. So 5 times 8 is 40. So 40 minus 40 is 0. So therefore, this should only have 5 bonding pairs of electrons. There should be no lone pairs on the central atom. And so when we draw this structure, we get this, and you see that there are no lone pairs on the central atom. Now let me just, I forgot to include the charge here. And you may ask, where does the negative charge come from? The negative charge, if you calculate the formal charge of silicon, it would be on the silicon. Now this wouldn't be a very stable structure because silicon, as you will learn next time when we talk about electronegativity, is not the most negative element. And so this would be a very unstable ion because silicon is less negative than chlorine, but it has the negative charge. So that makes it unstable. Next we go to ASH2 minus. Here it's best to draw out the Lewis structure. So we have a total of 8 valence electrons. So arsenic has 5, each hydrogen has 1, and we have a negative charge, total of 8. Now you have to remember that hydrogen only wants single bonds. So when we draw the Lewis structure, we have to make sure that hydrogen only has 2, and then the remaining electrons go on arsenic. So this is what the Lewis structure of ASH2 minus looks like. And so it has 2 bonding and 2 lone pairs of electrons. Next we get to xenon trioxide ion. And here there are actually two ways you could have done it depending on which rule you use, because no rule was specified. So if we look at using the octet rule, we get something that looks like this. And just to show you the formal charges, anytime you see an oxygen single bond, it's negative. And this is a positive 1 because the overall charge is negative 2. So here we have two bonding pairs. No, 3 bonding pairs, my bad. And 2 lone pairs. And then if we use formal charge, what we're going to do is we're going to take one of these lone pairs on a single bond oxygen and turn it into a double bond, because here the charge is negative 2. Negative 2 tells us we need 2 single bond oxygens. And so we get something like this. So the only difference is now one of the oxygens has a double bond. And so again, this oxygen is negative, this oxygen is negative 1, but now the xenon is 0. Excuse me, not that oxygen. This is actually, and this oxygen is 0, and this oxygen is negative. So now you still have an overall charge of negative 2. And I don't believe I put this answer choice as one of the correct answers in the question, but it is correct. So here you would have 4 bonding pairs and 2 lone pairs. Now you may ask, well, what about with molecular geometry? With molecular geometry, it doesn't matter which rule you use, you're going to get the same molecular geometry, because for molecular geometry, double and triple bonds only count as 1 pair of electrons. So in regards to molecular geometry, it won't affect your answer. So here again, we're looking at formal charge rules to draw an acid. So if you remember in the last session, we looked at the Lewis structure of chlorate. And we said chlorate has resonance because the double bonds can alternate between the single bond chlorine oxygen bond and the double bond chlorine oxygen bond. So we have resonance there. But now we want to draw the Lewis structure of an acid. And so when you have an oxoanion, such as in this case perchlorate, chlorate, sulfate, even nitrate, nitrite, the hydrogen is always attached to the single bond oxygen on the ion. So it's never going to be attached to the non-oxygen atom in the anion. It's always attached to the oxygen in the polyatomic ion, because oxygen, as we'll come to find out a little bit later on, is the most negative element besides fluorine. So that's why it's always attached to the oxygen. So now when we draw the Lewis structure, notice here that, again, adhering to formal charge rules, we have 3 chlorine oxygen double bonds and 1 chlorine oxygen single bond. And it's off the single bond that the hydrogen attaches to. And that's because if we were to remove this hydrogen, this oxygen would be a -1 and this hydrogen would be a +1. That's why they make a perfect couple, because this is -1, this is +1. When they come together, they're neutral. So we want to decide what would be a good description of the bonds present here. And so notice now that we have this hydrogen here, we no longer have resonance because this bond cannot flip back and forth because now it's locked into place. So with that said, since there's no longer resonance, then this chlorine oxygen is a single bond, whereas these chlorine oxygens are double bonds. And so the correct result here would be that we would have 3 chlorine oxygen double bonds and 1 chlorine oxygen single bond. And so the correct answer would be B. And so again, this is because now the hydrogen is attached, the resonance is gone. It can't flip back and forth. And so, but if we were to remove the hydrogen, then resonance would reappear because now that oxygen can go back and forth. So now getting into molecular geometry. So here it's important to draw the correct Lewis structure to get the correct number of bonding and lone pairs of electrons on the central atom. So for molecular geometry, we're only looking at central atoms of the ion or molecule. And so molecular geometry does differentiate between bonding and lone pairs, whereas electron geometry doesn't differentiate between the two. So here we have selenium pentafluoride. And again, you can use that little trick. So here we have a total of valence electrons of 42. And so we have 5 halogens. So each one's going to want 8. So 5 times 8, or excuse me, 42 minus 5 times 8 equals 2. So we're going to have 5 bonding pairs and 1 lone pair. Now, if we were to draw the Lewis structure, it would look like this. So we have 5 bonding pairs, 1 lone pair. So this has a total of 6 electron pairs around the central atom. So that would be, it would be one of the subsets of octahedral electron geometry. And so in this case, it would be square pyramidal. Next, we go to IBr2 minus. And again, there's a halogens on the terminal as the terminal atoms. So the total number of valence electrons, we have 1 times 7 plus 2 times 7 plus 1. And that's a total of 22. Now we have 22 electrons. We have 2 terminal halogens, so 2 times 8 means there's 6 electrons left over. So this structure would have 2 bonding pairs and 3 lone pairs. So again, this is a kind of a quick way to determine the number of bonding and lone pairs around the central atom. So now if we were to actually draw the Lewis structure, it would look like this. Just as we predicted, 2 bonding pairs, 3 lone pairs. Since it has a total of 5 electron pairs, this is going to be a subset of trigonal bipyramidal electron geometry, and this would be linear. So if you can imagine that if you have a sheet of paper and the iodine atom is sitting in the plane of the paper along with those 3 lone pairs of electrons. So they're sitting in the plane of the paper, and above and below the plane of the paper, you have bromine atoms. So those are 180 degrees apart from each other, and that's why it's linear geometry. Next, we have xenon trioxide. So again, whether you draw it based on the formal charge rules or octet rule, you're still going to get the same molecular geometry. So when we draw this, again, this was obeying the octet rule. You see that we have two bonding pairs of, two lone pairs of electrons on the central atom and three bonding pairs of electrons. Again, this is only the central atom that we're interested in. Now, if you were to draw it based on formal charge rule, there would be one of these oxygens would be a double bond. But again, you only count double and triple bonds as one electron pair. And so here we have a total of 5 electron pairs. So that's going to be a subset of trigonal bipyramidal electron geometry. And this would be T-shaped. So what it means is that the atoms form like a T. And then lastly, we have arsenic tetrafluoride ion. Again, here we have a halogen as a terminal atom. So we can look at the total valence electrons. So there's a total of 34 valence electrons. We have 4 halogens, and each halogen wants 8. So we have 2 electrons left over. So this is going to have 4 bonding pairs and 1 lone pair around the central atom. Now, if we were to draw this Lewis structure, it would look like this. So we have 4 bonding pairs and 1 lone pair. And this is referred to, since it has 5 electron pairs total, it's going to be, again, a subset of trigonal bipyramidal electron geometry, and it's going to be seesaw geometry. And again, if we were to highlight here, this is the apex, and then you would have a seesaw. So there's the 2 legs of the seesaw, and then the people going up and down on the seesaw. Okay. So here, this question wants us to look at bond angles and see which one of the following species has the smallest bond angles. So what you have to imagine is that when you start removing bonding pairs of electrons, which are all similar with lone pairs of electrons, it starts pushing the bonding pairs of electrons closer together. So what I'm going to do first is draw the Lewis structure of each one. And so here we have arsenic trifluoride, and you see that it has 1 lone pair and 3 bonding pairs. Versus if we had, for example, methane. Methane has 4 bonding pairs of electrons. So with 4 bonding pairs of electrons, the bond angle is 109.5 degrees. So that's with all 4 bonding pairs of electrons, tetrahedral electron geometry, 109.5. Now, when we went to arsenic trifluoride, we replaced one of the bonding pairs with a lone pair. So what happens now is that the lone pair pushes the bonding pairs closer together. And so this results in the bond angle being a little bit less than 109.5. So for example, it could be like 107, 108, 106. It depends on the size of the atoms as well. So we can note that it's going to be a little bit less than 109.5. Next, we go to NO2 minus. NO2 minus has 3 electron pairs if we're looking at it in relation to the geometry. So this would be what we call bent geometry. Now if we look at its cousin, boron trifluoride, so boron trifluoride has 3 bonding pairs of electrons, and the bond angle here, of course, is 120 degrees. Because they're all bonding pairs of electrons. So that means if we replace one of those bonding pairs with a lone pair, this lone pair is going to push these bonding pairs closer together. So what we can infer is that the bond angle is going to be a little bit less than 120 degrees, maybe 118, 117, 119, somewhere in that ballpark. Now we go to OF2. We draw the Lewis structure of OF2. We see that again it has 4 pairs of electrons around the central atom, 2 bonding and 2 lone pair. So if you look at methane was 109.5 degrees. Arsenic trifluoride was a little bit less than 109.5. And now since we have 2 lone pairs, they're going to push these 2 bonds closer together. So therefore, it's going to be a little bit or a lot more smaller than 109.5. So this could be like 104.5, 103.5, somewhere like that. So the more electron pairs you have, the more it's going to push the bonding pair of electrons closer together. Next we have tellurium fluoride ion. And so here we have 2 lone pairs, and you would think that these angles would be 90 degrees. However, since there's 2 lone pairs, they're going to push these bonding pairs closer together so that the bond angles would be less than 90 degrees. And then lastly, we have ICl2 minus. Again, this has 5 bonding pairs of electrons, but notice it only has 2 bonding pairs. So this is going to be 180 degrees apart. Because it's a linear geometry. Anything that's linear geometry, the bonding pairs are going to be 180 degrees apart. And for anything linear, you're going to have only 2 bonding pairs. So the one with the smallest bond angles would be D. And lastly, we just want to show you what happens when we have a molecule with multiple central atoms. How do we determine the geometry, the molecular geometry of those atoms? And by the way, with organic compounds like this, so organic molecule, organic compound, where you have lots of carbon and hydrogen, you're only going to go up to tetrahedral electron geometry. That means the most number of electron pairs you can have in a molecule is 4. That's it. So for organic molecules, you can't go beyond 4 electron pairs, which means you can't go beyond tetrahedral electron geometry. Likewise, with carbon, it can only be one of 3 geometries. Carbon can either be linear, trigonal planar, and tetrahedral. That's it. So carbon can never have, at least in Geochem 1, can never have lone pairs of electrons on it. It's always going to have bonding pairs of electrons. So it's either going to be linear, trigonal planar, or tetrahedral. And so that'll help you narrow down the answer choices quite substantially if you're asked what's the geometry of this carbon atom. Again, it can never have lone pairs of electrons on it. So we look at carbon 1. Carbon 1 has 1, 2. Remember, double bonds count as 1, 3 electron pairs. So C1 is trigonal planar because it has 3 electron pairs. Next, I'll come back to the oxygen. I want to do all the carbon first. If we go to C3, C3 has 1, 2, 3, 4 electron pairs. So C3 is tetrahedral molecular geometry. And C4 carbon, we have 1, 2, 3 electron pairs. So it's going to be also trigonal planar. You may ask, well, what would a carbon atom look like with linear? So it could be one of two things. It could be 2 double bonds. So a carbon with 2 double bonds, or a carbon with a single bond and a triple bond would have linear geometry. Next, let's look at O2. So with oxygen, most of the time, when it's a central atom in an organic molecule, most of the time, I would say like 90% of the time, it's going to be bent geometry. And the reason is because anytime you see an oxygen in the molecule as a central atom, it's going to have 2 bonding pairs and 2 lone pairs. So oxygen, the majority of the time, is bent. So these are some things you can remember to help quickly assess the types of molecular geometries in an organic molecule. Again, oxygen most of the time bent. Carbon is only going to have bonding pairs of electrons. Now, one thing I didn't show is the other common element we see in organic molecules is nitrogen. And this is going to show you some examples of what nitrogen can look like and how you can assess its molecular geometry. So here's one example of a nitrogen-containing organic molecule. Again, we see here nitrogen has 1, 2 bonding pairs, and 1 lone pair. And so here the nitrogen would be bent. And so if you see nitrogen with a double bond and a single bond, it's going to be bent geometry. Now for nitrogen, sometimes they show the oxygen, show the lone pairs, sometimes they don't. But it's understood that if it's not there, that the lone pair is there if you have maximum 3 bonding pairs of electrons. So this is one type of geometry nitrogen can have. It can be bent, again, when it has 1 double bond and 1 single bond around it. The other example of a nitrogen organic molecule is something like this. And here we see that nitrogen has 3 single bonds and 1 lone pair of electrons. And so here nitrogen would be trigonal pyramidal. And these are the most common types of, you could call them bonding motifs of nitrogen. So if you see a nitrogen with 3 bonds and 1 lone pair, it's going to be trigonal pyramidal molecular geometry. If you see nitrogen with a double bond and 1 single bond, it's going to be bent molecular geometry. And these are the most common, I would say, bonding motifs of nitrogen in organic molecules. So if you can remember these little tricks or these shortcuts, very quickly you can assess the molecular geometry of these types of atoms in organic molecules.